Hello, everyone, and thank you for joining us today. My name is Aaron Brister from Glenn Research Center, and I'll be your moderator for this webinar on the next generation closed Strayton engine design technology, hosted by NASA's Technology Transfer Program. In this role, I work with NASA scientists who have developed new technologies which may have applications outside NASA. We patent these inventions and market them to industry through our website, which I'll show you later. Our presenter today is Dr. Rodger Dyson. Dr. Dyson has worked at NASA Glenn Research Center for over 34 years developing power, propulsion, and thermal technologies, supporting both aeronautics and space missions. He currently serves as a power and propulsion technical lead, developing megawatt scale electric aircraft propulsion, hypersonic integrated thermal and propulsion applications, Mars nuclear electric propulsion, lunar surface power, and Enceladus robotic power. He is a prolific inventor with over 17 licensed patents. He previously served as Chief Technology Officer at Nirvana Energy Systems while commercializing one of his inventions. His most recent patent pending invention, and the topic of our webinar, the next generation closed Strayton engine design, received the Best Paper for Systems Award at the International AIAA IEEE Aviation Electric Aircraft Technologies Symposium, or EAT, conference in 2023. NASA Glenn was originally established in 1941 as an aircraft engine research laboratory, and this technology is a direct descendant of over 80 years of engine research at our center. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to Dr. Rodger Dyson.
Thank you, everyone. Thank you for joining. Yes, I'm Rodger Dyson, and I have the wonderful privilege today of sharing with you some technology that I think is going to be important, and look forward to collaborating with you in the future if you find this of interest to you. This is in essence an alternative to the current engine technologies that we're using. And it's, we call it the path to economic, national, and climate security. You'll see why, because when we talk about climate technologies, it usually comes at a cost, either the actual, financial cost or performance cost. But this technology can give you the climate benefits that we're looking for, while actually improving performance. So it's we get both of those parts of the benefit of the system. I'll just kind of go through quickly here the current technologies that people are developing or hoping can be used in the future with alternative fuels. So, for example, diesel and diesel electric are the two most used high-power technologies. They're compact, low cost, high efficiency, reliability, but their emissions are difficult to manage. There is some efforts to use hydrogen fuels to some fraction of the fuel being hydrogen, but really the only truly zero global climate impact emission technologies are batteries and the low temperature PEM fuel cells. The high temperature, for example, would still produce NOx. The battery option is being widely implemented right now, but again, it's relatively, due to its limited energy density, is suitable for really small systems. The fuel cell option is being heavily invested in right now, but it has a number of drawbacks, not to mention life, but also the size, the weight, and also its tolerance to fuel impurities as well as shock resistance. And then more recently, hydrogen gas turbines, are now being investigated and developed, but they do produce NOx even when used with hydrogen fuel. But it is complementary to fuel cells. It's cost efficient at large scale, can utilize lower purity hydrogen, and it has very good efficiency. But the technology I'm going to talk about today, I show in the chart here on the right. I compare fuel cells, diesel, gas turbine, and Stirling. Stirling normally wouldn't be in this conversation, except for the fact that this new technology combines gas turbines and Stirling together to form a new cycle called the Strayton cycle. So that's why I included it up here. And you can kind of see in all the different categories, whether it's life, efficiency over a wide range of loads, response to load changes, noise, vibration, power range, and emissions. It competes very well in all these categories with all these different technologies. So really, it allows you, it creates a new paradigm, and I'll explain, what this new paradigm is and the benefit to it. But I'll just start with this technology really is only useful today because we've been electrifying so much of the economy. If we didn't have batteries and fuel cells and other driving functions, as we head towards an electrified economy, then this technology would not work, because this is a closed cycle technology and its only output is electricity. And so if you don't have electric motors and all the rest of the vehicles that are already expecting electric power, then this technology, its time would have been too early. But it's very useful today because, obviously everything is electrifying. And like I said, batteries and fuel cells and other clean technologies have a number of drawbacks that we like to address. And I kind of show down here that, this is a technology where you get maximum performance with any heat source, and it's environmentally benign. I haven't explained that yet. And a lot of different parts of the economy are electrifying. And, here at NASA, we do aero as well as space, but also there's a large, off-road ground mobility activity, electrifying that area, maritime as well. So this technology can actually be used in all these different options. And you can achieve very high efficient performance, more efficient than fuel cells and diesel, while achieving a zero climate impact. And I'll discuss that soon. So we kind of we break it up into different areas when we talk about climate technologies. The more electric, the net zero, where we use carbon offsets or synthetic fuels, hybrid electric, zero carbon, where we use hydrogen combustion, but we still produce NOx. And true zero, this is kind of a vernacular that's used in the field. People refer to hydrogen fuel cells as being true zero, and battery electric. Well, I'm adding a new category here, and that's why I wanted to put this chart up, so you can kind of see, I think it's a new category, and it's a multi-fuel category. As we transition in the future, there is fuel anxiety. We really don't know what the infrastructure is going to look like, what's feasible, what the economy is going to support. Is it hydrogen? Is it ammonia? Is it synthetic fuels, biofuels? It's probably all of the above. And so having a technology that can support multiple fuels allows you to ride the waves of the future changes in the infrastructure. In other words, you can use this technology with today's fuels, and you can use this technology in the future with alternative fuels. It does that it's a closed cycle, and you can use any heat source, but in the case of transportation, you're going to use combustion. But we do a special kind of combustion, right? The multi-fuel flameless oxidation combustion, which is very hard to achieve with an internal combustion engine. Because in an internal combustion system, you've got flow rates to match, boundary conditions, a number of constraints, geometry constraints. So it's very difficult to implement flameless oxidation. But with a closed cycle, you can put the combustor on the outside, and now you can get a very clean system. And it's by reducing oxygen basically to 3%. And I'll talk about this further a little later. We also then, because it's essentially as a muffler rather than a direct exhaust, we can also recuperate the exhaust heat to desaturate the exhaust. So for example, for anything at high altitude, you'd like to remove the moisture so you don't create the contrails. And then finally, catalytic reduction. If you're not using hydrogen as your fuel, if you're using synthetic fuels, and some recent results, which I'll show soon, are suggesting synthetic fuels could be a very promising future as well. And we would remove the NOx with catalytic reduction. But I will say that the multi-fuel flameless oxidation reduces the work that the catalytic reduction system needs to do, because the flameless oxidation, because it has a very low oxygen content, naturally produces a lot less NOx. So it's not nearly as much to clean when you're done. And the idea is that you generate heat, and our closed cycle uses that heat to produce electrical power. And then your only exhaust is cold exhaust that's clean and unsaturated, essentially for a zero climate impact. If you use these other approaches where you have internal combustion, especially if you're going to be using hydrogen in the future, there's a lot of new problems with hydrogen, let alone the infrastructure, the risks of that fuel, flammability range, the pressurization 850 times when it expands from a liquid to a gas. You can't see the flame, gives off infrared, so you're getting sunburned and don't even know it. There's a lot of challenges with that. But that aside, there's also challenges with the engine, because when you flow the hydrogen through an engine, even when you combust it, you're still going to have all these effects I'm showing here: hydrogen embrittlement, a dual atmospheric effect. You get a larger temperature gradients, smaller flame wall quenching distance, higher flame temperatures, higher heat transfer coefficients. So there's it really changes your engine's life. And people today are trying to do this. We're trying to go from no hydrogen to gradually increasing the percentage of hydrogen to eventually people would hope to have 100% hydrogen. But it really has a lot of challenges to go in that direction. So this technology is very attractive. I'll just start with the performance. So the efficiency of this system can approach about 70%. And I'm comparing here a line of with diesel and fuel cells that have around 55% efficiency in a typical, advanced configuration. So we're able to compete with those two technologies on efficiency, and specific power and specific work is where it really starts to shine. For a lot of vehicles, batteries take up too much space. Fuel cells take up too much space. Diesel's been the go-to because it is one of the most compact engines out there. But you can see that with this technology, we can actually, be 2.5 times more compact than a diesel. So it's attractive from an efficiency perspective and also from a mass and volume perspective. And again, I mentioned earlier that one of the key features is the multi-fuel flameless combustion. And I'll talk about why it's enabled by this technology. And then because the emissions are naturally reduced with that form of combustion, it simplifies greatly, eliminating NOx and any water vapors that are in the exhaust. And again, we can use hydrogen with this system, and it's still preferred over internal combustion because at least now the hydrogen is kept outside the engine. But I'm thinking in the future that you're going to actually be using synthetic fuels that use hydrogen. I think the hydrogen will be used, you combine hydrogen and carbon dioxide to form synthetic fuels. I think that's going to be the longer term solution, because it's a lot easier to work with that kind of a fuel, and it's backwards compatible. But either way, we support any fuel. It's quiet because it's a closed cycle. So it's a very all you have is an external combustion heat source, and so all you hear is combustion. It's very efficient, as I'm showing in these charts. It's very compact. So this is a megawatt scale. 10 megawatt system is about 4 feet by 4 feet by 4 feet cube. I'll show that a little later. It's low cost, so we don't require the rare earths that fuel cells require, or batteries, and we don't need exotic materials. So we can actually utilize typical stainless steel materials. It's low maintenance. The system is sealed, so there's no oil changes. It uses gas bearings, and it uses its own working fluid to provide the lubrication. The working fluid is typically helium argon or helium nitrogen, or could just be argon. The lifetime, we never have gases inside the engine, and it doesn't degrade like a chemically reacting fuel cell or battery, both of which have a limited number of cycles or usage hours. This technology does not. And during the introduction, we mentioned that back in 1941, NASA was starting to look at turbo fans and so forth. Well, in the 60s, we actually had developed a closed cycle Brayton for space, because we needed something that could last for 20 and 30 years in deep space, for example. So these technologies are inherently intended to not require maintenance. And then it's scalable. It can scale, up to 50 megawatts down to 1 megawatt. It ends up being a very modular, compact solution. Each of these cubes is 10 megawatts, and you would stack these cubes, if you needed more power than that. So we're just real quick, it's very energy efficient. It can support fossil fuel and alternative fuels. It's scalable. Unlike Stirling, for example, which is kind of limited to about 25 kilowatts, this can go up to very high power levels. We can recharge and refuel with the existing and future infrastructure because we can use any fuel. We have no risk to our performance by using these alternative fuels because our engine is just collecting heat. It doesn't care about the fuel that's being used. It's just using heat. Because it's sealed, it can work in harsh environments. So if you're, near a ocean environment or other environments that normally would be hazardous, or dust environment, for example, in a desert situation, the engine is sealed from the environment. We want it to be able to support all operational needs, no loss in capabilities. This is where we usually lose out. If we use batteries or fuel cells, we kind of accept that as the price of a clean environment is, we want to have reduced. We're willing to accept higher costs and less performance. But this system, because it's sealed and it's a higher efficiency, that's 70%, we can actually achieve the clean environment benefits while we still have the higher efficiency. It's silent, like I said. The life cycle costs are very manageable. We don't have, again, exotic materials required. It can work with all of these different fuels, so it can even use today's infrastructure. And then you'll see that there's well-established training security programs in place because this new technology is combining two existing technologies that have been around for a number of years, but when combined, perform much better. So there is actually a lot of experience out there with the basic components of this technology. And then you can retrofit the system as well. So as more systems become electric in the future, we can replace engines with this system. So what is it? So what's this look like? Why is it able to do all this? In essence, it's a sealed engine that basically has a rotating compressor and turbine. And like I said, inert gases are used. There is an industry today using supercritical carbon dioxide, trying to generate power. So, there's definitely folks working that side, but it tends to be a high pressure system. In our case, we use, like I said, helium argon is probably the most cost effective, and we're low pressure, under a megapascal. And so it's a typical closed cycle, but the one thing you're noticing here is something's happening in the shaft. It's a sound wave. We're sending a sound wave or an acoustic wave through the shaft, and the sound wave is cooling the turbine. And it's actually, it ends up being a Stirling cycle, an acoustic Stirling cycle in the shaft. So it collects the heat from the turbine, converts that heat into a sound wave using thermoacoustics, and then rejects the waste heat into the compressor exit. And this is where you get the new cycle, because you have a Brayton cycle and a Stirling cycle working together, and they're both a bottoming cycle and a topping cycle for each other. So when you do a TS diagram, they actually are now, it's not just like a flow down from a Brayton cycle to a Stirling cycle. The Stirling cycle actually gives its heat back to the Brayton cycle. So it ends up being a Strayton cycle. It is a new cycle. Most of the power that's produced in the system is actually done on the Brayton side of the Strayton. But the Stirling side of the Strayton is providing a key thing, which is it's cooling this turbine. With typical closed cycles, it's very difficult to cool that turbine. Obviously, with turbofans, we have a lot of air on aircraft. We can cool the turbines, and that's why they've been improving over the years. But we don't have that luxury with a closed cycle. So typically, you have to bleed coal. You have to bleed the compressor gas off, and it really hurts your performance with these systems. But by combining these two different cycles together, we can achieve much higher turbine inlet temperatures. But the multi-fuel combustion I was talking about earlier is possible because this is a sealed system, and there's just simply a hot heat exchanger. That's the interface from the outside world to this sealed system. And so you have all the room in the world now to implement your combustion system. And now you can do what people have been trying to do for years, which is the multi-fuel flameless oxidation approach. And that's what allows you to have multi-fuel. And also now a lot lower airflow rates need to go through, because none of the air through this system goes through the engine. Whereas with an internal combustion system, you have everything from the combustor goes through the engine. But in this case, there's nothing from the combustor going through the engine. So it separates these two things. So you have external combustion, which enables this a clean multi-fuel process, and then the sealed engine. So a little bit more on this flameless oxidation feature. If you don't have the closed cycle with the turbine being cooled, you're typically limited to below 1200 Kelvin on the turbine because of creep and other effects of the materials that you're using. So typically that's where you try to keep it. But when you're in that range, you're only in the normal combustion range, and which means that you have a high oxygen content. And people have made these. This is and if you go back in time, you can see back in 1940, the open cycle path and the closed cycle path were actually very competitive. But as time went on, the open cycle outperformed the closed cycles because you could cool the turbines with the outside air, whereas with the closed cycles you could not. But now that we can cool the turbine using these sound waves, we can actually now compete at the same level as the large turbofans in terms of the temperature that we can operate it at. And when you do that now, you can operate with a flameless combustion regime because you're at a higher temperature, which allows you to operate at a lower oxygen content, which, as you can see down here, we compare lean premixed, lean direct injection, RQL, and then flameless based. And flameless based is superior in all ways, other than the fact that if you have an internal combustion engine, it's very difficult to actually implement. But this system eliminates that issue because we have, again, the combustors on the outside. And so we can operate at these much higher temperatures. So we now have the room that we need, we have the boundary conditions that we need, we have the flow conditions that we need to be able to operate in this flameless combustion regime. So it's inherently cleaner. So even if you use today's fuels with this system, in addition to being more efficient, because we're about 70% versus say 30 to 40% for most internal combustion engines, we're more fuel efficient, but more importantly is we're a lot cleaner when we are burning these fuels. So this is kind of a key takeaway, that because you're able to cool that turbine with a sound wave, you can all these other benefits flow from that. This is another chart that kind of summarizes, I think, the state of play for a lot of technologies. The axis down here is showing different technologies with different fuel assumptions. And right now, a lot of folks are talking hydrogen fuel is the answer and using fuel cells. And but when you plot the carbon dioxide, particulate matter, the NOx, and the contrails, at least for aircraft contrails, you have fog production actually on the ground, or even at higher altitudes, depending on how much hydrogen you're using, or you're reacting with a fuel cell. But now that we know in terms of climate change and global warming, that contrails and water vapor actually do contribute. They have a significant global warming potential. And also, hydrogen, people don't think about this, but hydrogen, if it's going to be leaking from, we're always going to have leaks, seals, if the whole world's using hydrogen, it has an 11 times higher global warming potential than carbon dioxide does. So, when you start putting all these different pieces together in a practical system, that's why I've got listed down here synthetic fuels or power to liquid fuels that are the EU actually just passed legislation where by 2050 they want 35% of all their fuel for aircraft to be PTL produced, not hydrogen. PTL, and PTL requires hydrogen to make. So just basically you're combining carbon dioxide with water or hydrogen to form the PTL fuel. And you can see that when you look at all of the different relative emission components, it's only the closed cycle Strayton that gets you to the zero climate impact, because you're able to process the moisture out of the exhaust, for example. Because again, we're not in the engine, we're outside the engine. So we can do more things with it. We can recuperate, but to desaturate the exhaust, and we can also use selective catalytic reduction to remove a little bit of NOx that's produced from the flameless oxidation. Batteries are the only other alternative, but batteries, even with the recent RPE Propel 1K initiative, is still going to provide a limited percent of electrification for large vehicles. So if you want to go large vehicles, megawatt scale, or mining equipment, things like this, this seems to be the only option to be able to achieve this. But we can work with hydrogen, and we can work with synthetic fuels, and we can work with today's fuels as well. This is the key, though. This fuel flexibility, you don't hear too much about it, but this is a result out of Germany, just came maybe 3-4 months ago, comparing synthetic fuels with liquid hydrogen. And turns out synthetic fuels can actually be cleaner than the hydrogen when you include the effective contrails and other things. So this got me thinking, and I'm thinking more and more that we're going down the hydrogen path because we think fuel cells are the answer. We hope with additional development, and we hope that batteries can keep improving. But this technology I'm showing you here today, it's really a new player. It gives you a new way to look at the problem, and we really don't know what the future fuel is going to be that's going to be optimal from a techno-economic perspective. And so having a technology that can work with hydrogen or PTL or today's fuels, it could really be a game changer in terms of not having to reinvest because your technology you've invested in guessed wrong on what the future fuel is going to be. So here I kind of compare single fuel versus multi-fuel electric systems. And again, most of the systems today are internal combustion. I'm suggesting external combustion because it allows you to do the flameless oxidation. The internal systems have maintenance, the oil changes, things like this. There's no maintenance other than changing a filter for the combustor, because that's the only thing that's exposed to the environment. Everything else is sealed. There's obviously the noise from internal combustion engines. Of course, that's managed with mufflers and things, but we don't generate the noise. We're a sealed system. Definitely produces greenhouse gases of one kind or another. We can actually take it down to zero climate impact because we have full control of the combustion stream, since it's not inside the engine. And a lot of these solutions are less than 50% efficient when you take the full system efficiency, and we're higher than 50% efficiency. Just kind of a quick comparison. Also, it's scalar, modular, and extensible, so it can work in the altitude environment. As aircraft becomes electrified. That's actually where I started developing this for, because these other technologies were not what we needed for larger aircraft in particular. But it can also be used for harsh environments. So for example, brackish water areas. Also off-road equipment, so mining equipment, agricultural, construction. There's a huge impetus all across the world right now to electrify that market. But a lot of people complain, well, where am I going to find a place to charge my stuff? Where am I going to be able to, it's an off-road environment after all. So we're giving them the ability then to use today's fuels and as well as future synthetic fuels, so they really don't have to change their operations, right? It's going to be the same way of operating as they're used to, and hopefully actually saves them some money because this would be a more efficient solution. So how does this work? I'll go through this in a little bit more detail. I mentioned earlier that we have a sound wave that travels through the shaft and it cools the turbine, and we reject the waste heat into the compressor exit, and it forms a new cycle called the Strayton cycle. Okay. And if you're not familiar with thermoacoustics, I have a couple of charts where I'll quickly explain that. One key thing about these closed cycles is the turbines are very small. A megawatt scale system, the turbines are only about 6 inches to 8 inches in diameter. And because they're so small, you can conductively cool them using these sound waves. If they were very large turbines, we couldn't probably use this approach, but they end up being very small. So that's one of the benefits of a closed cycle as well, is the turbo machinery gets to be very small. Again, we're using gas bearings, so they're just floating on their own working fluid. And then because we can have a higher turbine inlet temperature, the Brayton part of the cycle gets to be more efficient, but we also can use that flameless oxidation, like I was saying. I'm going to pull up a video since it's a lot easier to show you rather than tell you. So this is what the package looks like. There's 3 acoustic layers to this. All right, so there's a sound wave that travels through this top level. There's a sound wave that travels through this middle quad, and then there's a sound wave that travels through this bottom quad. Okay. the turbo machinery is in this middle quad, all right, and there's 4 of them, and they're actually connected. So it ends up having a 4-stage compressor and a 4-stage turbine expansion. It turns out with closed cycles, that's the knee in a curve for efficiency, is 4 stages for compression and 4 stages for expansion. So it turns out that the Brayton part of the cycle naturally wants to be arranged in groups of 4 like this. And most of the power is produced actually at these generators here. Roughly each of these is going to be limited to about 2.5 megawatts. So that's why this whole system is about 10 megawatts, because you have 4 of them. But you can, of course, scale down lower. But as you go higher, you start needing different kinds of turbines, and other properties start occurring that make it more difficult to implement this approach. So this is about a 10 megawatt system. But if you needed more of them, you could stack them together, because they're 4-foot cube size. And then these are heat exchangers on the inside here, recuperators and so forth. But I'll play the video so you can kind of see what it looks like on the inside. These are actually acoustic generators. It turns out that you can collect the acoustic energy using these bidirectional turbines. And again, these have gas bearings in them. The working fluid is the same everywhere. So the sound wave that's traveling through here is also the same working fluid that the flowing part of the fluid is, where it's spinning the turbine. So that's helium argon spinning the turbine, but it's also we have stationary helium argon in these quads, and that's actually sound waves we're showing. So with a sound wave, you're not actually, there's no fluid flowing, it's the energy that's flowing. All right, and you can see that the sound wave, and there's a heat exchanger in the shaft that's collecting the heat from the turbine. And then here we're doing interstage cooling. So between each compressor stage, we need to cool. Normally you just waste that energy and it's not very useful. But in our case, we convert that energy into a sound wave and generate some electrical power from that. You can see it's mostly hollow tubes. So it's not expensive actually to add these systems, to add these acoustic systems. And we're able to then to have a bottoming cycle to the Strayton cycle. So the Strayton cycle is basically in the middle quad. And then the bottom quad ends up being a bottoming cycle for the interstage cooling. Here we're showing the combustion air coming in, being preheated, and it's actually also being used to help generate the sound wave. I'll talk about that, the thermoacoustic effect, in a minute. All right, and then on top here we're showing a combustor. You can also use solar heating. You could also use nuclear heating. But obviously for transportation applications, you're going to use the fuels. And this top quad is actually collecting the waste heat from the combustion process. Not all that combustion gas, thermal energy, makes it into the sealed engine, because heat exchangers are maybe 90% effective when they're well designed. So this ends up being a topping cycle then to the Strayton cycle. So you have the Strayton cycle on the inside, and then you have 2 thermoacoustic Stirling cycles on the top and the bottom. And that's how you're able to get the overall very high efficiencies, because you're synergistically using all the thermal energy without adding a lot of mass or complexity to the system. They're mostly just hollow tubes. Okay, so that's kind of a quick overview. We do have publications on this, so you can dive more deeply into the equations and how we derive things. So now I'm going to talk a little bit more, because not a lot of people are familiar with both these technologies. Either you might know something about closed Brayton, you might know something about thermoacoustics, but they're really different fields, and not a lot of people are expertise in both of these. So multi-stage Stirling engines, typically you would use a 4-piston Stirling engine to increase the power. And that's been done in the past. They've actually driven trucks with this system, but it has these kind of clumsy moving parts, and it needs to be lubricated and so forth. But it does eliminate the need for a flywheel. If you only had 1 piston, like the first engines back in the early 1900s had 1 piston, and you needed a large flywheel because you only had power in part of the cycle. And if you wanted the piston to return, you had to use the momentum of a flywheel to push it back up. But when you use a multi-piston engine, even in V8s or V6 engines, now you have power throughout the whole cycle, because you're linking these in series. But you have, again, linkages and moving parts. Well, with thermoacoustics, you can do the same thing, but you get rid of all the moving parts. In other words, all we have is a hot heat exchanger and a cold heat exchanger. And thermoacoustics is a field in which if you have a hot area and a cold area, it'll amplify a sound wave. So as the sound wave travels through the tube, it gets amplified, and then it travels around the tube, gets amplified again, travels around the tube, gets amplified, and it reaches a peak based on the size of the heat exchangers. So it quickly amplifies, and because we have 4 of them, all 90 degrees apart from each other, we don't need a resonator, we don't need flywheels, we don't need these things, very similar to the 4-piston engine I just showed, which shrinks the size of this down significantly. And it turns out that a 60 hertz system, which is about optimal for these thermoacoustic systems, ends up being a quad shape that happens to be the same size as what the closed Braytons also want. Remember earlier I said the closed Braytons had 6-inch diameter turbines, even at megawatt scale. Well, then so they geometrically match each other. They both want to come in groups of 4. This to get rid of the flywheel, and the groups of 4 with the Brayton to have the optimal compressor and turbine performance. And then so they geometrically fit together. So you needed that to happen. If they don't geometrically fit together, you are out of business. And a little bit more on the thermoacoustics. So if you have heat coming in, you can generate a sound wave, and then some of the waste heat goes out. But if you have a sound wave, you can also use it for refrigeration. That's another key point of this, is that we're cooling the turbines and we're generating electrical power, but we can also use this to cool parts of the vehicle. So it's kind of it's a power system and a cooling system integrated together. And this is a close-up view of if you have a sound wave, you can generate electrical power with these bidirectional turbines. This was actually pioneered in the Netherlands by Kees de Block. So give credit to him. So in terms of heritage components and TRL level, so the acoustic Stirling that I'm describing, there's actually a company in the Netherlands called Sound Energy that's selling these units right now that's very much based on this principle. They've been in business about 2 years. So it's a pretty new thing. They're installing these on rooftops of buildings to provide cooling of their buildings. All right. And then, of course, we've had turbo machinery and Brayton, especially, and the microturbines have been done in the past. And so what we're doing is we're taking 2 known technologies that aren't widely known. There's not a lot of closed Brayton, and there's not a lot of acoustic Stirling, and it's really not taught in schools, but in combining them together to form this system. And again, they just happen to synergistically fit together. So over here, I'm showing the 4 Brayton systems that are all connected together, and you only need 1 recuperator because you have when you have 4 of these together like this. Recuperators are usually the heaviest part of the system. That's another benefit to grouping this into a quad loop of 4, is then the heat exchangers are 25% of the size they would have been otherwise. And that's this dishwasher size thing I'm showing in here. And then again, the acoustic Stirling, we have 3 of those. This collects the combustion waste heat. This collects this cools the turbine, and this collects the intercooling heat. So it looks more complex than it really is. It's mostly hollow pipes with a sound wave traveling through it. But the point is that there are companies that manufacture these things already, and we're combining 2 things that already exist into something that actually performs a lot better. This is what it looks like when you assemble it. So you've got the first acoustic quad layer, put the second one on it, which has the turbines with it. Then you put the combustion acoustic quad on the top. You add the heat exchangers, and you add the plumbing. And that's basically your system. And it ends up being roughly about 4 feet by 4 feet by 4 feet for a 10 megawatt unit. So some key takeaways. This technology has the unusual situation or benefit of allowing you to achieve 0 climate impact if you use hydrogen or if you use synthetic fuels of the future. But it also gives you, because you're using flameless oxidation, but it also gives you superior vehicle performance because you get much higher efficiency than the fuel cells and the diesel options that are out there now, and it's more compact. So this is, to my knowledge, this is the only technology where you're not asking the customer to accept lower performance while trying to improve the climate. It's scalar scalable and modular. Basically, you could stack these things together, and because of that, you can avoid an abrupt S-curve change in technology and budgets. You can use today's fuels. You can use the future fuels. You can stack these for different power levels that you need, and it's compatible with the existing infrastructure. And I think that's huge. And that allows this to be supported through different political climates too. The reality is every country in the world has different politics at the time, different emphasis, but this appeals to both. If you're trying to improve the climate, or if you're trying to save money and have better performance, this technology does both of those things for you. So it's kind of apolitical from that perspective. This also allows our industry to focus on a single fuel type. Keep using your fossil fuel, but let's switch it over to a future synthetic version as soon as possible. Okay. But it's, and these future synthetic fuels can also work in today's legacy engines. So that's what I think is going to be the winning hand. But again, that's my opinion. But this approach recognizes that industry already has an inertia and life of its current fleet, whatever industry we're talking about. Nobody wants to, get rid of all the stuff they have now and start over. And this allows you to use today's infrastructure and vehicles while positioning you to then, adopt cleaner technologies in the future without having to reinvest. Yeah, and it's competitive because it maintains today's performance and cost expectations, but it does have a clear path to zero climate impact. We can achieve net zero CO2 with the existing fleet with synthetic fuels while achieving a superior performance. But we can also achieve zero climate impact by using this flameless oxidation, and the post-processing, post-emission controls that we're able to get because the combustion system is outside of the engine. So this can be used, like I said, as the world's electrifying. This is just leveraging the fact that the world's electrifying. If the world was not electrifying, this technology wouldn't have its place. It'd be too expensive to implement. But the world's already going this direction. We're already electrifying so many different things. So this ends up being just an alternative to, say, batteries or fuel cells, or partially hydrogen internal combustion engines. This gives it's a new player in the field to compete with these other technologies in an electrified market. So aerospace, automotive, marine, generators, and then in general clean energy applications, backup power. And I'll just remind everybody that this has a long heritage, because when I trace this back, the first closed Braytons, actually, 1961 was the first closed Brayton, the ML1 by the U.S. Army. They operated for a year or two, but a lot of these things just never quite took off. It was always like a government project. And again, until the economy became electrified, there wasn't really a benefit to this sort of a technology, because people aren't going to electrify just because you have this new technology. But we have an opportunity now to leverage all the things that are going on now, including hydrogen production, and the whole momentum that's going in that direction, with a system that can work with all these different fuels and give you more and better performance. So just in summary, thank you very much for your attention. You can probably tell I'm excited by this technology. There's a lot to it. We do have some very detailed papers that are published out there about this. This is just a high-level summary of it. Definitely looking for feedback, looking for partners. But in short, it's a multi-fuel system that can achieve the zero climate impact while still being low cost, scalable, quiet, and hopefully improving the performance of what people today expect from their equipment. So thank you very much.
Okay, hi again, everyone. This is Aaron. Great presentation, Rodger. Thank you. So we've received several questions, and we'll get to them shortly. But first, I'm going to provide a brief overview of NASA technology transfer process. To access technologies like the next generation closed Strayton engine design through the NASA Technology Transfer Program, you can search for them using NASA's Technology Transfer Portal. All of NASA's patented technologies are listed in the portal at the website shown at the bottom of the slide. When you go to the portal website and begin to scroll down, you'll come to the section shown here that allows you to search for technologies using keywords. You can view more information on any of the patents in our portfolio. You will find buttons up here to ask a question and apply to license. As you continue to scroll down the technology description page at the bottom, you'll see a download fact sheet as a PDF link, which is highlighted here. Clicking on this will allow you to download the full fact sheet. If you click on the Ask a Question link during your search, you'll be taken to the page shown here where you will find in the information, or you will fill in the information about yourself and your company and ask whatever questions you have about the technology. This questionnaire will go directly to the NASA Agency Licensing Concierge, who will review your questions and get back to you with answers. This slide illustrates the NASA licensing process. Once you find a technology you're interested in on the portal, you can apply for a patent license through an online system called Atlas. A link to Atlas is provided in each technology description, as you saw in slide 4, where the apply to license link was shown. Once an application is submitted and accepted in Atlas, the terms of the license agreement can be worked out with a NASA licensing specialist, and the license will be executed between NASA and the partner. All right, we received a lot of questions here. So thank you to everyone that has submitted questions so far. Feel free to continue submitting your questions by typing them into the chat box. If you have any questions about, or for me, about my licensing presentation, I can answer those as well. If we do not get all the submitted questions, if we not get to all the submitted questions today, then we will follow up with you by email afterwards. Okay, so let's see here. Okay, so can we have a joint patent with NASA if we manufacture a project in collaboration? So this question is more about partnerships. So NASA has various ways to partner. What we're talking about here today is licensing. And so when you license something, you're getting specific patent rights, which will allow you to practice the invention to certain limits. And that's the primary way to partner with what we're talking about here today. However, there are partnership options, which are called Space Act agreements. You might be more familiar with CRADA, which is a cooperative research and development agreement. A lot of the federal agencies use those. We at NASA use Space Act agreements. And under a Space Act, if we were to partner in a collaborative partnership under a Space Act, then we could potentially have a joint ownership in an invention. But that's one way that could occur. Generally, though, if you are licensing from us and then you invent something in addition to what you've licensed, that's yours. We retain our rights to the patent, the licensed invention. Okay, what is the TRL for this technology?
So the two individual components, the acoustic Stirling and the closed Brayton, have actually been at least TRL 5. And in the case of the acoustic Stirling, it's a product in the Netherlands. So I guess you would call that TRL 9. The combination of both of these together is TRL 3. So the individual components are high TRL, but we have very detailed 3D, verified models of this system. So for example, we've got whole system models. We've also derived the efficiencies in a specific work I was showing you earlier. Those can be directly derived in our paper from last year at the conference. Goes through that derivation, and it shows how where that came from. We've also done the CFD, finite element analysis. We've done all of the 3D work on the areas where we needed 3D work. For example, demonstrate you can cool the turbine. We've also recently built in-house at our center the acoustic Stirling. We built a full-scale version of that. We're actually using it for thermal management of aircraft. but we've built that system. So all the same design tools that we're using, everything we've built to date has worked very well. But I'd have to put it at TRL3 for the integrated system. And so it definitely, I think we're looking for partners who understand the technology, and understand that there's a good deal of work here, but we're trying to show the promise is probably worth the work.
All right, we have another question here. How does scalability of the unit relate to size? For example, does a 100 kilowatt unit also need to be a 4x4x4 layout?
No, it shrinks down. Um, uh, and that 4x4, that's being generous because all of the acoustic tubes that I'm showing there, they don't need to be straight lines. You can actually spiral them. It's just for ease of explaining and showing people that we have them as straight lines. But in our lab, we've actually spiraled them together. So we've taken for example, if you have a 20-foot long tube and you serpentine spin it, you can have it become a foot long. So the sound wave itself, yeah, it's going to want to have about a 20-foot length to it. But in terms of the physical dimensions that would represent, you could spiral that and shrink it down. The turbo machinery also doesn't change much. You're going from maybe a couple inch diameter to maybe a 7-inch diameter, and you get a very wide range of power output from that. So yeah, you probably wouldn't want to use this, below, I don't know, 25 kilowatts or something like that. But again, just like the automobile engine, and multiple people are making, they've over the years we've compressed them and they fit. The same thing with this. This is going to evolve over time, and each company that works with this is going to find the best way to make this as compact as possible. But yeah, in principle, the physics of it can be very flexible because the sound waves do not need to travel in straight lines.
All right. Has a prototype been built and tested yet?
Yes. So the integrated part of this, the closed Brayton and the acoustic Stirling, that's TRL3, meaning that we have the design for it. We can actually, if we have a partner, we can provide all the specs, turbine designs, the bearings, all the things that go into it. The only thing that's been physically tested is the closed Brayton and the acoustic Stirling. And like I said, those have been tested separately. And it's the combined part where we have analytical solutions and we have 3D, CFD, and FEA analysis. The very next step would be for a partner, perhaps working with us to build a prototype, combining these two systems together. There's a lot more that I don't have time to go through today to give confidence for why we've done a lot of risk reduction. There's something called the HEM motor, which has a rotating cryocooler in it. There's a number of different things that we've been doing that have reduced the risk for each of these parts and pieces. So the next step is putting the whole system together.
All right. There's one question here. It says, can the presentation be accessed for study purposes? And we're going to send all the registrants this video link in about a week. I was going to say that towards the end of the closing statements here. I suspect you could study it from the presentation, but perhaps we could consider providing a copy of the slides as well. Let's see. What platform is it trialed and tested on, please? What platform is it trialed and tested on, please?
Yeah, the combined closed Brayton with the acoustic Stirling is a high fidelity 3D engineer model of the system. The components have been demonstrated. The individual components have all been demonstrated. And like I said, the acoustic Stirling is being sold in the Netherlands by a company called Sound Energy, and in the U.S. there's a number of micro turbine companies in the U.S. that can make the turbines and the gas bearings and and these various components. So it's there's nothing here that people don't know how to make, in other words. And so we are kind of anticipating that we'd have to work with partners on this that bring their expertise in these various areas. There's no one single part to this. There's the bidirectional turbines, there's the high-speed generators, there's the gas bearings, there's having the properly designed turbine and compressor, flameless oxidation, catalytic converter, all of this. It's just think of an automobile engine type effort. If you were to from scratch try to build an automobile engine, there's a lot of parts and pieces that go together, but you do it because there's an economic benefit to it when you're done.
Okay, we're getting close to the end of the hour here. Let's see if we can get through a few more. Someone missed how this, let's see, they didn't understand how propulsion is generated and how it can be used in aerospace applications.
Yeah, so in propulsion, it has no value unless you have an electrified economy with electric motors, because this is going to generate electrical power. But what's happened just in the past couple of years is we now have megawatt scale motors that are very compact that can use this power. So whether it's for aircraft or mining equipment or marine vessels, everybody's developing electric motors that needs power. And they're using batteries and fuel cells, they think, is the only zero emission path for doing that. So this is really an alternative to batteries and fuel cells, particularly at the higher power levels that's needed for the larger vehicles that are out there. So yeah, it's because the economy has electrified or is electrifying that this new technology now has a market.
Okay, you say that it reduces NOx, but how does it do that if it uses a multiple fuel oxidation inlet?
Yeah. So so flameless oxidation, was accidentally discovered in the late 80s, and they use it today in a lot of different industrial applications. Flameless oxidation has a lower oxygen. So normally when you're burning something, you're at 20% oxygen. With flameless oxidation, you're operating about 6 times lower oxygen, so about 3%, and at these higher temperatures. So you naturally have a less of the oxygen available to form the NOx and the SOx and other, other global warming gases. So by using flameless oxidation, you're minimizing the pollution from your fuels, okay? And because we're not inside the engine, we can actually better purify the exhaust that comes out. So we can recuperate the heat. We can actually take out the moisture from the exhaust, and we can take out the NOx using selective catalytic reduction, so SCR in the exhaust. Now, with a typical internal combustion engine, that's a lot harder to do because you've got to have all of the airflow rate going through the engine too. So you don't have as much flexibility. In our case, we only need enough air to burn the fuel. We don't need the air to move a piston or move a turbine, right? All we're using the air for is combustion, and we have a full control of the combustion flow path. So in addition to the flameless oxidation process not generating a lot of pollution to start with, which makes it easier then to filter out any remaining pollutants that are in the exhaust. And of course, if you use hydrogen, you're really talking about NOx and water, moisture, water vapor. In the case of synthetic fuels, you're going to have carbon dioxide coming out, but that's the whole idea, is that you're using synthetic fuels. You're collecting the carbon dioxide from the atmosphere when you produce it, so you're net zero on the CO2, but you're also eliminating the NOx and the SOx by having that really low oxygen content combined with post-emission filtering or controls. So that's how you do it, and it ends up being effectively you can't say zero emission, but you can say zero climate impact.
Hold on, let's skip around for a minute. If we could hang out for maybe 5 more minutes, we might be able to get through a bunch more here. We'll try. Is that all right, Rodger?
Yeah.
Okay. Someone asked, what is the estimated rough order of cost?
Yeah, so I think it's gonna track about $142 per kilowatt in full production. once you've amortized factory costs and all the rest of that kind of thing, and you've got, which is basically the cost of turbo generators where they approach.
Okay, another person asked, or they stated that when they've been working with acoustic sound waves, they can't achieve more than 10% heat transfer. Can you discuss the cooling mechanism a bit more?
So with thermoacoustics, I kind of went through it quickly, but you're roughly at 50% of Carnot when converting the thermal energy into a sound wave. So for a really well-designed system, you're about 50% of Carnot, and Carnot depends on the high temperature and the low temperature that you're working with, and then you're about 15% of Carnot on the cooling side. All right. However, remember, for cooling the turbine, we're not using a heat pump, right? We're actually using another cycle. So all of that energy from the turbine goes into the Stirling cycle, all right? And the cooling is happening because the engine itself needs that heat, all right? So, so when we talk about cooling, there's two different kinds of cooling happening here. There's the cooling of the acoustic Stirling cycle, the heat engine side of it that's collecting the heat from the turbine because the cycle needs it, all right? And then there's also, if you wanted to provide additional cooling somewhere else with the sound waves that are generated, then you're going to be about 15%, maybe 20% of Carnot for the heat pump side of that.
Okay. How is mass streaming or Gideon streaming, I think I may have butchered the pronunciation there, Gideon streaming handled? Gideon.
So in this case, to have the Gideon streaming, that's a very common problem if you have a single stage and you have a compliance loop and it's oriented the right way. Okay. In this case, we are a quad structure, and I actually know David Gideon very well. And he's the one that discovered Gideon streaming, and he designed and built the Sage modeling tool that solves the Navier-Stokes equations, and he was able to predict that Gideon streaming would happen. Well, we're using actually his design tools to verify the performance of this system, and so we know we don't have the Gideon streaming because the inventor of the software and the discoverer of Gideon streaming, his tool is saying we don't have Gideon streaming. So hopefully that's convincing, and it's just the structure of the system. We have 4 stages forming this loop, and it's a fairly large loop, whereas and we're fairly small diameters between the stages. If you look at the heat exchangers, they're fairly large size, but the inertance tubes or thermal buffer tubes that connect them are a pretty small diameter. Whereas if you look at some of the Greg Swift work from the past, those are pretty large diameter systems that they were working with. So which made it more likely for Gideon streaming to happen. So hopefully that answers that. And if you want more detailed analysis of that, I can provide that.
I'll do 2 more. What temperatures of excuse me, what are the temperatures of the fluid entering the turbines?
Yeah. So to get that 70% efficiency, we're assuming a temperature ratio of 7. So for aircraft up at altitude, 240 Kelvin is about the temperature at roughly 35,000 feet. Multiply that by 7, that would be the high end temperature. So 1800 Kelvin, 1900 Kelvin, somewhere in that range. So that's the turbine inlet temperature, but the materials don't see that temperature because we're actively cooling those temperatures with our acoustic Stirling cycle. And that's really the point, is that we can run with higher fluid temperatures because the materials don't see those temperatures.
All right, last question. What inspired you to combine the 2 traditional thermodynamic cycles into one?
I've been thinking on this for almost 10 years now. It takes a long time to learn thermoacoustics, and it takes a long time to learn turbo machinery. And we've been actively trying to solve these problems for aero and space missions. and none of them are very good. I mean, we look at a lot of stuff worldwide trying to advance these things, and they always have a gotcha. And even this, my first attempt at Strayton, if you look in the literature, you'll see there was an open cycle Strayton that I had another group analyze, and it was okay. It was 10-15% better than a simple Brayton system, but it had a lot of mechanical issues. It was going to be really hard to implement. So this is just a case of just working at it, and getting rid of the problems as you go. And once I realized that these two quad structures fit inside each other, that was golden, right? Because they didn't have to. They don't have to be the same geometry and be so synergistic. Like you can't do this with three. You can't do this with five. You actually need four. That's why it's called the closed Strayton quad generator. So I think it's a very unique property of these two different fields that enable this to be so attractive.
All right, great answer. Okay, so that's all the time we have for today for questions. If we did not get to your question during the Q&A session, then we will follow up with you by email within the next week. If you have additional questions, please feel free to email them to me at this address. We'll be sure to follow up. We will send a recording of this webinar to all registrants within 1 week. Once again, we really appreciate you taking the time to be with us here today. Thanks, everybody.
Thank you.